Hello everyone, I'm Martin from Wolfram Language group, and now it's time to talk about what new features we plan for the fluid dynamics in the next version of the Wolfram language, the 15.0. But before we start, I would like to briefly revisit the current status of the fluid dynamics and also the latest additions to the fluid dynamics. So the fluid dynamics is probably one of the newest additions to the PD modeling. We added it only recently in version 14.0 when we added the fluid flow PD component and the laminar flow monograph. The fluid flow PD component is our main tool for fluid dynamics, and it allows you to easily generate the partial differential equations that are used for modeling fluid flow. The laminar flow monograph is our main monograph for the fluid dynamics. And if you are already familiar with the finite element method and the Wolfram language and would like to start exploring fluid dynamics, this is a good place to start. Then we added the blood flow modeling in a cerebral aneurysm application example. And this is our first application example, which features non-Newtonian fluids. And the goal of this application example is to predict where a certain aneurysm is going to rupture. In the latest version, 14.3, we added support for axisymmetric and swirling flows, and also we added a new monograph, the fluid dynamics model verification tests. Since this version was released quite recently, I would like to revisit those additions in more details. So the axisymmetric flow is a flow in an axisymmetric domain, and the axisymmetric domain is a domain with rotational symmetry. So it has some axis of symmetry, and if we rotate the domain around this axis, such as this axis Z in this example, then the domain won't change. In such a case, we can rewrite the equations into cylindrical coordinates. So instead of using x, y, and z, we use radius r and angle theta, and the z component stays the same. We can then assume that the flow does not depend on the angle theta, and that the angular velocity component is equal to 0, and we then obtain the axisymmetric equations. So here we have an example with the fluid flow PD component. The fluid flow PD component has two arguments. The first are the variables, and the second argument is the parameters. For the variables, here we specify the velocity and the pressure. So the first component in this case is the radial component of the velocity. The second, since we assume that we are dealing with axisymmetric flow and we assume that the angular velocity is equal to 0, so we set the second component to 0. And the third component, that's the velocity component in the z coordinate. And the last, finally, we have the pressure P. The velocity components and the pressure depend on the radius r and the z, and but they do not depend on the angle theta. For the parameters, here we prescribe the viscosity, density, and we set the region symmetry to axisymmetric. And with this, we obtain the axisymmetric equations. So modeling axisymmetric flows is quite easy in the Wolfram language. All we have to do is basically just take the fluid flow PD component and slightly modify the variables and set the region symmetry to axisymmetric. In case you want to keep this angular velocity non-zero, you can do that. That's perfectly fine. In such a case, you obtain the swirling flow. So here we have a symbolic example. So here we have the variables that, but once again, none of the velocity or the pressure actually depend on the angle theta. And for the parameters, instead of setting region symmetry, we set the coordinate chart to cylindrical. So now let's have a look at a numerical example for the axisymmetric flow. So here we have a narrowing cylindrical pipe, and the flow in this pipe is driven by a parabolic inflow. So even though we are actually dealing with a three-dimensional problem, we only set up the domain as a two-dimensional, because we assume that this domain has an axis of symmetry, which in this case is this left edge. So this is the benefit of the axisymmetric equations, because now instead of a 3D problem, we are dealing with just 2D problem. This allows us to reduce the amount of unknowns in our equations. So the equations are solved faster, and they require less memory to solve. So after we set up the domain, we set up the equations using the fluid flow PD component, and then we set up the boundary conditions. The first boundary condition is just a parabolic inflow here at the bottom. Then we have a no-slip boundary condition here on the right-hand side. The no-slip boundary condition means that we assume that the velocity is equal to 0, so the fluid sticks onto the boundary and there is no slip. And then we have on the top and here on the left we have the outflow boundary condition and the excess of symmetry boundary condition. The final boundary condition is for the pressure, and this is here to obtain unique solution. Then we solve the equations using ND-solve, and here I would like to point out this interpolation order. Here, this is called the Taylor root finite element, and it's probably the most common and most popular finite element in the fluid dynamics. Here, we set the U and W to start the components of the velocity to be a piecewise parabolic, and the pressure is set to be piecewise linear. Once we have the equations, we can plot them using, for example, the vector plot for the velocity. And for the pressure, here we have a 3D visualization because, well, we are dealing with a 3D problem after all. The second addition to the Wolfram language after the axisymmetric flow is the new monograph, fluid dynamics model verification tests. And this monograph features 5 benchmarking tests with references. The first test is a stationary 2D flow around the cylinder. The goal of this test is to compute a traction and drag acting on a cylinder in a narrow rectangular channel. Second benchmark is a stationarily driven cavity. This one also features non-Newtonian fluids. And the last stationary test is axisymmetric flow in a cylinder. This one is comparison with exact solution. Then we have 2 time-dependent tests. The first one is axisymmetric flow in a cylinder. The second one is flow in a cube. And both of them are comparisons with exact solution. So now let's move on to what we plan for the next version. And in the next version, we decided to focus on post-processing. We decided to simplify and streamline the process of obtaining additional information from the solution of the equations. And in the fluid dynamics, what you can try to compute from the solution is, for example, the viscosity and stress. So we added 2 new functions, the fluid viscosity and fluid viscous stress, which basically achieve this. But before I show those 2 functions, I would like to start first talking about the equations so that we actually know what the viscosity and the stress is. So let me write the equations in this form. So the first equation is basically just the balance of momentum. Here we have on the left-hand side, we have inertial forces, and on the right-hand side, here we have this divergence of this sigma. The sigma is the stress tensor and is composed from 2 parts. The first is just minus pressure times identity matrix, and the second part is called this one. The second part is called the viscous part of the stress tensor, or just viscous stress tensor. And this viscous stress tensor is equal to the 2 times viscosity times this epsilon with a dot, and which is the strain rate tensor. And the strain rate tensor is just a symmetric part of the velocity gradient. The last equation that we have here is the divergence of velocity. That's just balance of mass, and it means that the fluid that we are dealing with is incompressible. So now let's go back to this viscosity. Viscosity is basically just an internal traction in the fluid. So if you imagine, for example, 2 different layers of fluid flowing at different velocity, then this difference in the velocity naturally creates a friction in the fluid. And this is basically what the viscosity is. If we assume that the viscosity is constant, then we are dealing with Newtonian fluids. On the other hand, if we assume that the viscosity is not constant, we obtain non-Newtonian fluid. And in such case, the viscosity depends on the quantity that's called the shear rate. Once we have the viscosity, we can try to compute the viscous stress tensor, which is basically stress that's caused by the viscosity. So Now let's move to the first function that we plan to add in the next version, and that's the fluid viscosity. As I said, we plan to add two new functions for viscosity and stress. The viscosity is this mu in this in the viscous part of the stress tensor, which is this this expression here. So the first function is the fluid viscosity. This function computes the fluid viscosity, and it has three arguments. The first are the variables, second argument is the parameters, and the last argument is the velocity. So here we have an example for Newtonian fluid. The variables here are the standard variables that are utilized by the fluid flow PD component, and the parameters are also the same that are used by the fluid flow PD component. The velocity is just the solution to the equations. Well, so velocity in this case is u and v. As I already mentioned, the Newtonian fluid is a fluid with a constant viscosity. So in case of the fluid, in the case of the Newtonian fluid, the fluid viscosity just returns the dynamic viscosity. So the fluid viscosity is kind of a boring function for Newtonian fluids. But this changes when we consider non-Newtonian fluids. And here we have an example of the power law fluid. Here, to set up a power law fluid, for the parameters, we specify this fluid dynamics material model, we set it to power law, and then we set up the material parameters for the power law fluid. And the formula for the viscosity of the power law fluid is the following. And in this formula, what you can see is are the spatial derivatives of the velocity. So here the viscosity depends on the velocity. So it's something that must be computed once the solution is actually known. The second function is the fluid viscous stress, and this function computes the viscous part of the stress tensor. Once again, we use the same. It has the same arguments as the fluid viscosity. So first we have the variables, parameters, and then we have the velocity. Here we have an example for Newtonian fluid. Once again, the variables and parameters are the same as that the fluid flow PD component uses. The output of the fluid viscous stress is a stress tensor, which is symmetric. So the output is a symmetrized array. And here we can see it in the matrix form. For power law fluid, we obtain basically something similar. Here what you can see is basically here what you can see is basically something similar that we had here for the Newtonian fluid, that is the spatial derivatives of the velocity, but the only difference here is the viscosity. Instead of constant viscosity mu here, we have the power law viscosity here. So now let's take a look at a numerical example that uses those two functions. And here we have a non-Newtonian flow in an opening channel. This example uses once again the power law fluid, and this is the domain that this example uses. Here on the left-hand side we have an inflow, so the fluid flows into the domain here, and on the right-hand side we have outflow, so the fluid flows out of this domain. So first we set up the domain, then we set up the variables and parameters, and then we use the fluid flow PD component and ND solve to generate and solve the equations. And once we have the solution, we can compute the viscosity. And for this, we of course use the fluid viscosity. Here, I would like to point out one thing. The unknowns of the equations are solved for the velocity and the pressure. So the output of the ND solve is not only the velocity, but also the pressure. So the fluid flow result features the velocity and the pressure. But the viscosity and the viscous stress, they do not actually require the pressure. You can compute the viscosity or the pressure with even without knowing the pressure. They only depend on the velocity. So it's not necessary to pass actual pressure to those functions. But to make it more convenient for you, we added the possibility to just take directly the result of the ND solve with the pressure and put it directly as the last argument of the fluid viscosity. So once we have the viscosity, we can use, for example, the contour plot to visualize it. Here we see that the viscosity is largest here in the center, and it's getting lower near the boundary. This is called shear thinning, and it's a common phenomenon in non-Newtonian fluids. Next, we can compute the viscous stress. So here we utilize the new fluid viscous stress function. Once again, we use the full fluid flow result with the pressure. And once we compute it, we can plot it once again, for example, using the contour plot. But here, since it's a viscous stress is a tensor, we plot just the norm of the stress. The last thing we can try to compute is the total stress. So the total stress tensor is given as the viscous stress, and then we subtract the pressure times the identity matrix. And once again, here we have the visualization of the total stress. So those are the two new functions that you can expect in the next version of the Wolfram language. And in the remaining few minutes, I would like to also briefly talk about our plans for the version 15.1. So if we, for simplicity, just talk about Newtonian fluids, that is fluids with constant viscosity, that are incompressible, then what we currently have implemented in the Wolfram language are the Navier-Stokes equations, which can be obtained by using the fluid flow PD component. In the version 15.1, we would like to add additional types of equations like the Stokes equation and Oseen equations. The Stokes equations are basically a simplification of the Navier-Stokes equations. If we assume that the flow does not depend, that there are no inertial forces in the flow. So it's the way how it's done is that we remove this term. The advantage of the Stokes equations is that they are linear, so they are really easy to solve, and it's much faster to solve them. Something in between the Stokes and Navier-Stokes equations are the Oseen equations, which are obtained from the Navier-Stokes equations by replacing this velocity by this steady flow velocity V0. This steady flow velocity is something that's given, that's something that's known, and it's usually something that's known by the boundary condition. Common example here, common application of the Oseen equations is a flow around some obstacle. So let me summarize our plans for the future. In the next version, 15.0, we plan to add two new functions, fluid viscosity, which computes viscosity of a fluid, and fluid viscous stress, which computes the viscous part of the stress tensor. You will be able to find examples of those functions in the laminar flow monograph and on the ref pages of those functions. And if you would like to see some more difficult, something coming from real life, then we plan to update the cerebral aneurysm with those two functions, and which will utilize those two functions to predict the rupture site. In the version 15.1, we plan to add the Stokes equations and Oseen equations. So that's all from me. I hope you have learned something new, and if you have any questions, feel free to ask.